For this lesson, we're starting our next unit, but we're really just continuing with trigonometry. In this lesson, we're going to be looking at the idea of equivalent trigonometric functions. And we've already discussed these informally throughout our previous discussions on trigonometry. The first and easiest way to talk about equivalent functions, and it really helps if you understand or if you can bring to mind the graphs, the pictures of the graphs. Sine and cosine are both trigonometric functions with periods of 2 pi. So that means you can phase shift these by any multiple of 2 pi, whether it's 2 pi or negative 2 pi. That could also be 4 pi, 6 pi, 8 pi, any multiple, any integer multiple of 2 pi, any integer multiple in the positive or negative direction. Now, generally, we don't use more than one period on either side of this to make our point, but this could be any value. This could be 2, 4, 6, 8, 10, etc. This could be negative 2, negative 4, and so on. For the tangent function, we have a period of pi, and so in that case, it's going to be integer multiples of pi that cause this pattern to repeat itself. And similarly, in the case of sine and cosine, the reciprocal functions that go along with that. So this is also going to apply to, it's not working properly. Let's try that again. Cosecant theta, this would work for secant theta in the sense that they have periods of 2 pi, and cotangent theta has a period of pi, so it's also going to repeat on those intervals. So that's the first way when we talk about equivalent functions. What that's saying is that the results that you get using sine theta, sine of theta plus 2 pi, sine of theta minus 2 pi, etc., you put in a value for theta, you're going to get an indistinguishable result. So that means these are equivalent to each other. We can also look at the symmetry of functions, and we can come up with some equivalent expressions that way. So if you recall, when we talk about the symmetry of a function, we're talking about even or odd symmetry. The standard definition for even functions is that f of x is equal to f of negative x. In other words, the original function can be horizontally reflected and we get the same result. For an odd function, there are two definitions, but the one that I'm referring to here is that a horizontal reflection of the original function is the same as a vertical reflection of the original function. You could also, for odd, you can also say that the original function is equal to negative f of negative x, which says that the original function is a horizontal and vertical reflection will give you the exact same thing. So here, if I start with cosine, here's one period of cosine written or drawn in blue. I can reflect that across the y-axis. That's a horizontal reflection, and you can see I end up with the exact same in red. So that reflection is still part of the cosine curve, because this whole curve, which I've drawn in black, is the cosine curve. So cosine of x is the same as cosine of negative x, because that is an even function. In the case of sine and tangent, we have what's known as rotational symmetry. So here we have sine, which starts at 0, 0 and starts by going up to the right, and then here we have a rotated sine, which is going down to the left. But both of those lie on the parent function for sine. Another way to look at that rotational symmetry is we could imagine reflecting sine horizontally, which would give the first crest would look like that, and then if we reflected that vertically, we would end up down here in this trough. And so once again, we have symmetry. And that applies to both sine and tan. So that's another way to come up with some equivalent functions. Now, another way we can do this, a third method we can come up with some equivalent expressions, is using the idea of complementary angles. So using the idea that angles which add to pi by 2, which is the same as 90 degrees, have some properties. So let's just fill these out and you'll get an idea of what I'm saying here. You've seen this before. You've probably seen this before in the context of angles measured in degrees. So the sine of pi by 3, I've got my special triangle here, the sine of pi by 3 is root 3 over 2. And what else is equal to root 3 over 2? Well, if we take a look, the sine of pi by 3 is root 3 over 2, but the cosine of pi by 6 is root 3 over 2. So I could have written this as the cosine of pi by 6. The cosine of pi by 3, is 1/2. But what else gives me a value of 1/2? Well, that would be the same as the sine of pi by 6. So I could write this one instead as the sine of pi by 6. And you can probably start to get an idea, but so can you anticipate the tan of pi by 3? What is that going to relate to in terms of pi by 6? So what is the tan of pi by 3? The tan of pi by 3 is opposite over adjacent. That's square root of 3 over 1. And so what is going to be the equivalent in terms of pi by 6? So in terms of pi by 6, that's going to be, to get root 3 over 1, I would need adjacent over opposite. And if tangent is opposite over adjacent, then cotangent is adjacent over opposite. So this becomes the cotangent of pi by 6. And then from there, we can extrapolate some of these. So if the sine of pi by 3 is the cos of pi by 6, then the cosecant of pi by 3 should be the secant of pi by 6. And we can verify that. The cosecant of pi by 3, well, that's 1 over the sine of pi by 3. So sine of pi by 3 is opposite over hypotenuse. So the cosecant of pi by 3 is hypotenuse over opposite. So that would be 2 over root 3. But what else is going to give us 2 over root 3? Well, that would be the same as the hypotenuse over the adjacent for pi by 6, which is in fact secant. And then this one is going to be the cosecant of pi by 6. The secant of pi by 3 is the cosecant of pi by 6. The cotangent of pi by 3 is the same as the tangent of pi by 6. And in general, what we get from that is that the general rule here is that the sine of theta is the same as the cosine of pi over 2 minus theta. So just think about that. The sine of pi by 3 is the same as the cosine of pi by 2 minus pi by 3. So for example, let's just redo that. The sine of pi by 3 is equal to the cosine of pi by 2 minus pi by 3, which is the cosine of, these need a denominator of 6, so that's 3 pi by 6 minus 2 pi by 6, which is equal to the cosine of pi by 6, which is what we deduced earlier. So carrying on from there, sine theta is equal to the cos of pi by 2 minus theta. Cosine theta is equal to the sine of pi by 2 minus theta. Tan theta is equal to the cotangent of pi by 2 minus theta, and so on. I'm not going to write out all of these. Now, one legitimate question you might ask here, you might say, well, hold on, these were all acute angles. Does this only apply for acute angles, or does this apply everywhere? And so just to try to address that very briefly, I'm certainly not going to give a comprehensive proof for this, but let's start with this one. Sine theta equals cos theta of pi by 2 minus theta. So let's put on just a very rough sketch of sine theta. So there's sine theta. And what I want you to think of is this expression, if I extend this page a bit, this expression, this is just a transformed cosine. So if I take this, and in particular I take the cosine part, the cosine of pi over 2 minus theta is the same as the cosine of negative theta minus pi over 2, isn't it? So what that's saying is take the cosine, which looks like this. So that's going to look something like that. If I reflect that, then I'm going to end up over here. So there is my reflected cosine. And now I shift that to the right, pi by 2. But that takes this value up to here. It takes this value, so let's put those in like this. It takes this value over to here, here, and you can see here and here. And so I end up with this. And notice that when I did this one, and that's right on top of my original blue sign, this has nothing to do with the value of theta. So this equivalent expression, sine theta equals cosine of pi by 2 minus theta, that equivalent expression is true for any value of theta, any real number. And so it's going to turn out that all of these can be shown to be universally true for any values of theta. Now you do have to watch out when you're dealing with tan and cotangent because of restrictions. Okay, so we do have restrictions on theta, but other than those restricted areas, for example the vertical asymptotes, this is true for any value of theta. Okay, and then another way we can do this is using the primary and related acute angles. The primary angle is essentially your theta value, and then we try to write that in terms of a related acute angle, and we apply the cast rule. So let's take a look here. So let's imagine that I've got theta minus, I've got pi minus theta. Pi minus theta, essentially, if I go over here, that's pi, and then I come back, that's theta. So this value that we're talking about is, in essence, this angle right here. Pi minus theta is this angle right here. Well, how would we solve, if I call this angle alpha, how would we solve for the sine of alpha? We would say that it is the same as the sine of the related acute angle. But what's the related acute angle here? That related acute angle is actually theta. But the cast rule says that sine is positive over here. Okay, so that tells me that the sine of pi minus alpha, or the sine pi minus theta, which I've labeled here as alpha, so pi minus theta is the same as just simply the sine of theta. The cosine of pi minus theta is going to be related to the cosine of theta because theta is the related acute angle. But because of the cast rule, I know that's going to be negative. The tangent of pi minus theta is going to be related to the tangent of theta, but because of the cast rule, I know tangent is negative in that quadrant. Similarly, I can do this for any of these. So in this case, I'm going to get the sine of, now what's this one going to be? This is pi plus theta, and we know that's going to be related to the sine of theta, but because of the cast rule, this is going to be subtracting. The cosine of pi plus theta is going to be equal to the cosine of theta, but because of the cast rule, it's going to be negative. Again, theta is my related acute angle here. And the tangent of pi plus theta is going to be the tangent of theta, the tangent of the related acute angle, but cast rule says that tangent is positive here, which we don't, of course, we don't normally write that as positive. Let me just try that theta one more time. And finally, over here in quadrant 4, we get the sine of, now what's this angle going to be? This one is going to be 2 pi minus theta. Sine of 2 pi minus theta. And that's going to be related to the sine of theta. And because of the cast rule, I know that sine is going to be negative. Cosine of 2 pi minus theta is going to be, because of the cast rule, positive cosine of theta, and tangent of 2 pi minus theta is going to be, because of the cast rule, negative tangent of theta, of the related acute angle. So a bunch of equivalent expressions there. Another one, in this case, I've really kind of gone through this already, which is because of sine and cosine and tangent and cotangent and secant and cosecant, because these different pairs look very similar to each other, you can take any pair that has the same general shape and you can verify pretty much any property you want to using those transformations. So I already did this as an example. I showed you this earlier. So I showed you that here to show you that sine theta equals cosine of pi over 2 minus theta. I showed you that very roughly using transformations. And we could do that with any transformations that we wanted to. I've lost my, there we go. Okay, so that's it for this lesson, and good luck with that homework.